The room is dark except for one clean line of light, a graph on a screen. A decade of radial velocity measurements, each point a tiny confession from a star. The dots don't shout. They don't even speak in full sentences. They lean, they drift, and then quietly, unsettlingly, they bend the other way. A long, patient trend that seems to reverse itself as if the data changed its mind. Somewhere on that same timeline, a flare blooms from Proxima Centauri, brief, violent, and bright enough to leave a scar in the record. Over Proxima B, that flare doesn't just light the scene, it seems to rewrite it. In the title's promise, Flare over Proxima B, flip the RV drift. The real reason in decade data. The word flipped is the hook. The credibility test is the point, because gravity doesn't flip, but our measurements can. We call Proxima B an exoplanet because the light from its star is telling us indirectly that something is tugging. In radial velocity, we infer a planet from tiny shifts in a star's spectral fingerprint, minute changes that look like motion toward and away from us. That's the clean story. But here the story is being told by an active red dwarf. And an active star is never a silent background. So what does it mean when an RV drift appears, then seems to flip across a decade of data? It could mean the star is moving under the pull of a planet, and our first models just didn't capture the whole orbit. It could mean there is more than one influence in the system braided together. Or it could mean something more unsettling, that the star's own stellar activity is acting like a ventriloquist throwing its voice into the measurement. This is the tension that shapes everything we'll do next: signal versus artifact, planet versus star, detection versus interpretation. Because if we can't tell whether the wobble belongs to Proxima B, we can't responsibly climb the ladder to what people really want to know: whether this nearby world could hold an atmosphere, whether it sits in a habitable zone that matters, whether any future claim about a biosignature is grounded or built on sand. Here's the plain language truth: RV is like listening for a steady bass line under changing noise. A planet's tug should be regular. A star's behavior is not. Spots rotate in and out of view. Bright regions come and go. Flares erupt. And every one of those can deform the very spectral lines we treat as our ruler. On an active star, magnetic events can change line shapes and depths. So the spectrum shifts not because the whole star moves, but because the light pattern changes. That's not motion, it's contamination. And contamination can imitate motion so well, it earns a name we never use lightly: false positive. So we hold the flip up to the light and ask the only question that matters right now: what kind of reality could produce it without breaking physics? A reversal in the long-term modeled trend often points to a changing contaminant, something like an evolving activity pattern, rather than a planet abruptly doing the impossible. The flare becomes a suspect, not because it proves anything on its own, but because it shows the star's capacity to distort our view. It's a reminder that the measurement is made of light, and light can be shaped before we ever translate it into velocity. This is where the decade matters. A short data set can flatter you. It can let you believe that a partial curve is the whole truth. A long data set is more honest and more dangerous. It gives you the baseline to see slow changes you would otherwise miss. It also gives slow changes room to masquerade as planets. Evidence moment: the plot itself. A decade-long sequence of RV points that first leans one way, what looks like drift, then bends, then leans the other. That's the visual anchor, the calm betrayal of a trend that won't stay put. And alongside it, a flare spike in time and event that says plainly, this star can alter what we're measuring on short time scales, even as we try to read a long one. We don't get to declare what's real yet. In this section, Our job is to frame the mystery honestly. RV is a real hard-won method for finding exoplanets. It has delivered worlds we trust because it has been tested against itself, against time, against other diagnostics. Active M dwarves can counterfeit RV signals through line-shape distortions, driven by magnetic behavior spots faculae flares. A flip in apparent drift across decade data fits a scenario where a changing activity environment, or the way we modeled it, tilts the interpretation from planet-like trend to star-like trend, or vice versa. It is possible that multiple weak influences are braided together planet tug plus stellar rotation harmonics, so early fits assign the wrong pieces to the wrong causes. But there's a hard guardrail we won't step over. We will not treat habitable zone as a synonym for life. Not here, not ever. The habitable zone is a distance and an energy balance, a first filter, not a verdict. Any talk of signs of life, any future biosignature or technosignature depends on whether we can measure and subtract the star's mischief. If we can't, the most exciting claim becomes the easiest one to fool. So we put the flare and the flip into a box labeled possible confounder, and we name it clearly stellar contamination. Flares and evolving magnetic patterns can imprint changes that masquerade as Doppler motion. That's the concrete test we have to run before we trust the shape of the drift at all. And the title's promise stays in view the real reason. In decade data, the real reason might be a planet. It might be the star. It might be the subtle interplay between them and our assumptions. But the only way to find out is to open the black box and watch how starlight becomes velocity step by step until we can see exactly where a flip could be born. We turn from the graph to the light itself. Because to decide what flipped, we have to learn how radial velocity is made from spectroscopy and where it can be made to lie. The spectrum appears like a barcode drawn by nature, thousands of thin dark lines carved into starlight. It's beautiful in the way fingerprints are beautiful, not because they're decorative, but because they're specific. Proxima Centauri's light carries its identity in these lines. And for radial velocity, those lines are everything. We take that starlight and ask a brutally narrow question: are the lines shifted even slightly compared to where they should be? The premise is simple motion changes the wavelength of light. A star tugged by an exoplanet should show a tiny Doppler wobble, a rhythmic in and out that repeats with the planet's orbit. But what we actually measure is not motion in space. We measure changes in a spectrum. And that difference is where the uncertainty lives. This is the section where we earn the right to use the word flipped without turning it into a metaphor. Because when the title says flare over Proxima B, flip the RV drift, the real reason in decade data, the real reason is never just one dramatic point on a graph. It's the entire pipeline, the conversion of light into numbers, holding steady night after night, year after year. Here's what turning starlight into radial velocity really means in human terms. First, you need a reference, a ruler. RV is extracted by comparing an observed spectrum to a reference pattern, some representation of what the star's lines look like when you're not fooled. That comparison can be done by matching templates, masks, or models, but the basic act is the same: align one fingerprint to another and measure the offset. Second, you need stability. The difference between planet and nothing can be smaller than the changes caused by temperature shifts inside the instrument. The detector, the optics, the wavelength calibration, these are not background details. They are the stage the entire play is performed on. If the stage tilts, the actor looks like they moved. That's the tension pair in plain language: model fit versus calibration drift, signal versus artifact, evidence moment, the timeline of observing seasons. Not a dramatic montage, just the quiet fact that decade-long data sets are stitched from many nights, many conditions, sometimes even different calibration regimes. A long baseline is powerful because it lets you see slow effects. It's also treacherous because slow effects can hide inside it. So when we look back at that decade of ARV points for Proxima B, and we see a drift that seems to flip, we have to consider a possibility that sounds mundane, but can be decisive. Instrument systematics changes in wavelength calibration, detector behavior, thermal stability can imprint false trends that look like astrophysics. And here's the key idea for an audience that doesn't live inside equations. If you change the ruler, you change the measurement. Sometimes the ruler changes suddenly, an update in the pipeline, a shift in how the spectrum is referenced. Sometimes it changes slowly, an almost invisible creep that only appears when you look back across years. Either way, the output can mimic the thing we're hunting. A planet-like drift, a planet-like curvature, even a flip if one segment of the decade is calibrated slightly differently than another. But we can't just blame instruments and move on. Because around Proxima Centauri, there's another ruler that changes constantly, and it's not in the lab. It's on the star, still in this how we know section. We stay disciplined. We keep the mechanics clear without pretending they eliminate uncertainty. Our V is not a single line sliding back and forth. It's thousands of lines, each one with its own noise and sensitivity. We average information across them to gain precision. That averaging assumes the lines behave consistently, that their shapes don't change for reasons unrelated to motion. Over long baselines, the method becomes sensitive not just to planets, but to slow star-driven changes and slow instrument-driven changes that can masquerade as drift. Even without changing hardware, different analysis choices, different pipelines, different priors can redistribute what looks like planet versus what looks like activity, producing an apparent reversal in the model trend. This is where we acknowledge the uncomfortable truth that sits under every confident detection plot. The data do not interpret themselves. We do. And our interpretation is only as honest as our accounting of what could mislead us. So we name the confounder for this section plainly without hiding it. Inside jargon instrument systematics, wavelength calibration shifts, detector effects, thermal drift, the kinds of errors that don't announce themselves with a warning light, errors that show up only when you ask the data to remain consistent across a decade. And that brings us back to the title thread, because it's not just a flare happened, it's that across a decade of RV drift something flipped, and the credibility question is whether that flip is astrophysical or procedural. If the star's light went through a subtly changing ruler, the drift can reverse without anything in space reversing at all. Now we tighten the story. Because even if the instrument were perfect, Proxima Centauri wouldn't be. Around red dwarfs, the star itself can write false motion into the spectrum. And the stakes extend beyond, is there a planet? They reach into the next rung of the latter atmosphere. Retrieval. Claims about biosignature chemistry that can be mimicked by contamination. If we can't diagnose what the star and the instrument do to starlight, then later, when we read faint atmospheric features, we won't know whether we're seeing a world or seeing the star's fingerprints bleeding into it. So we leave the lab and turn to the suspect that doesn't hold still, even in principle. We confront the star as a moving part of the measurement flare spots and chromatic distortions, because that's where a flip can be born without any planet changing its mind. The flare is not a metaphor. It's a physical event, an eruption of magnetic energy that turns a quiet red star into a sudden hard light. For a moment, Proxima Centauri doesn't just illuminate its system, it overwhelms it. And on our graph, our careful decade of radial velocity points that moment, sits like a bruise in time. Now we make the promised turn. The change of perspective isn't philosophical, it's methodological. We stop treating the star as the background and we treat it as the signal. Because if the title is true, flare over Proxima B flipped the RV drift. The real reason in decade data, then the flare isn't merely noise. It's a clue about what the measurement is vulnerable to. A flare is the star declaring in public what it can do in private, reshape its light without moving its center of mass the way a planet would. This is the tension pair that matters here, said in plain language: planet signal versus stellar activity, motion versus distortion, detection versus interpretation. What does a star do that can counterfeit motion? It stains its own spectrum. A star is not a uniform glowing ball. It's a surface with magnetic weather, dark spots, bright faculae, active regions that come and go. As the star rotates, those patches slide across the face. We see changing which parts of the star contribute most of the light at each moment. That changes the shape of spectral lines, how deep they are, how skewed, how symmetric. And RV pipelines are exquisitely sensitive to line shape, because a line shape is where the velocity is extracted. So the trick is cruelly simple. If the star's lines warp, the algorithm can interpret that warp as a shift, a false Doppler signal, a false positive. With Proxima Centauri, that risk isn't theoretical, it's the daily environment. And this is where the decade-long baseline becomes a different kind of story. Over long times, the star isn't just flaring, it's evolving. Its magnetic patterns can change their character: more spots, fewer spots, different latitudes, different lifetimes. If the model RV drift seems to flip across years, one plausible driver is not a planet reversing anything but the star changing the pattern of its contamination slowly enough to look like a trend, dramatically enough to look like a reversal. Evidence moment, the split-screen logic the outline demands. RV on one side, activity proxies on the other. Flare, brightness line shape indicators rising together in the same epochs. Not because it proves causation by itself, but because it gives us a test. Does the RV anomaly track the star's temper? When it does, it's a warning. It says you may be measuring the star's face, not the planet's pull. Now the case tightens around Proxima B itself. Proxima B matters because it sits in the star's habitable zone, at least by distance and energy balance. That phrase, habitable zone, carries hope. But here, hope has to pass through physics. Around a flare-active red dwarf, the question isn't only whether the planet exists, it's whether the environment permits an atmosphere to persist, and whether any future atmospheric spectroscopy can be interpreted without being hijacked by the star. 2 calibration sentences and then we return. On Earth, the sun's variability matters, but it doesn't usually dominate every measurement of the planet's existence. Proxima Centauri is different, small, close, and magnetically loud. And in exoplanet science, the loudest foreground can drown the faintest truth. So we keep the honesty tags close. Stellar magnetic activity can create apparent RV shifts through line shape changes and chromatic effects, especially in active M dwarfs. Activity can be tracked with indicator signals in the star's light that rise when a magnetic disturbance rises, and those indicators can correlate with RV anomalies. A flip in the long-term trend is consistent with an evolving activity environment that changes the sign or shape of the contamination term across the decade. Some residual patterns might also be explained by additional weak companions, but only if activity-based explanations fail strict diagnostic tests. Now we name the confounder. This section is built around explicitly as required time variability versus sampling, because even if you have the right diagnostics, the timeline matters. Observing isn't continuous, it's seasonal. There are gaps, there are windows. sparse sampling can alias a star's rotation and activity cycles into longer apparent trends. A periodic signal can masquerade as another period if you only listen in fragments. That's not speculation. It's a known vulnerability of time series inference. And across a decade, that vulnerability can compound into something that looks like a slow drift that later flips when in reality it's the same star seen through different windows. So what do we do with the flare? We don't treat it as the culprit. We treat it as an interrogation lamp. It tells us the star can change quickly. It forces us to test whether the RV drift is stable in a planet-like way or whether it's braided with activity. It forces us to ask when we subtract the star what remains. And the reason this matters for the search for life is immediate. If stellar contamination can masquerade as motion, it can also masquerade as chemistry. It can imprint wavelength-dependent features that later confuse atmosphere retrieval and inflate the risk of biosignature false positives. The chain is unbroken. If we can't trust the star subtraction in RV, we must be cautious about star subtraction in transmission or emission spectroscopy. The title's hook stays in the foreground. Across a decade of data, the RV drift flipped. The credibility framing is the whole point. The real reason might be that the star changed its face, and we mistook that changing face for motion. And now we reach the edge of this section's purpose. We've made the star a primary actor. We've admitted that the measurement is a contested space where planet and star can mimic each other. Next, we do the only responsible thing left. We assemble what the decade actually allows us to conclude calmly, conservatively, without letting the mystery choose its own ending. The screen goes quiet again. No flare now, no flash to distract the eye. Just the long record a decade of radial velocity points the gentle scatter, the slow bend, the unsettling moment where the drift seems to flip. In this light, the story stops being dramatic and becomes something harder accounting. This is the cosmic checkpoint, not a celebration, not a verdict. A pause where we ask what the data truly permits us to say about Proxima B and what it does not. Because the title's promise is not simply that something happened. It's that across a decade of data, the RV drift flipped, and there is a real reason. The honest version of that promise is this. The real reason might be a planet, it might be stellar activity, it might be instrument systematics, or it might be our own model assumptions reshaping the partition between them. And if we care about atmosphere and signs of life, we don't get to skip this step. So we start with what's firm. Radial velocity is a method that has found real exoplanets by measuring tiny repeatable shifts in stellar spectra consistent with orbital tugging. It is not an artistic interpretation. It is measurement translated through calibration and models. Around active M dwarfs, those measurements are vulnerable to contamination flares, and magnetic regions can distort line shapes in ways that mimic motion. Now the checkpoint question becomes practical after we account for the star's behavior and the instrument's stability. What remains that is best explained by a planet-like signal? And what parts of the decade-long drift, the part that seemed to flip, are best treated as contamination until proven otherwise? We don't pretend we can answer with perfect clarity. We answer with the best current conclusion that survives the most conservative reading of the outlines chain, separate what looks planet-like from what tracks activity or systematics. Then keep the uncertainty visible. In the visual language of this section, we layer the story. A planet term, the portion of the RV behavior that repeats with the stability we associate with orbital motion. An activity term, the portion that correlates with diagnostics of stellar activity or shifts in ways consistent with evolving surface patterns. A systematics term, the portion that could plausibly arise from calibration drift or other instrument level biases. This isn't decorative. It's the only way to keep ourselves honest, because the danger in a compelling curve is that it invites a single cause story, a planet end of sentence. But the reality is a mixture, and the mixture changes over time. Evidence moment, the peeling apart image, one curve becomes 3 stacked components. The point isn't that we know every term exactly. The point is that the decade-long record demands we try. And when we do, the dramatic flip looks less like physics reversing and more like a model learning late what it was missing, that the star's contribution is not constant across the decade. So here is the conclusion. Stated in the tone the data earns calm, bounded a little ominous. Proxima B remains an exoplanet candidate supported by RV periodicity, as described in the broader scientific literature. In this episode's frame, that support is inseparable from how we handle stellar contamination. A flare-associated flip in the model long-term drift is more consistent with changing stellar activity or systematics terms than with any planet changing its gravitational signature. Gravity doesn't flip. Our partitions do. The most defensible stance is to treat portions of the long-term drift as contamination unless they remain after aggressive cross-checking with activity indicators and stability diagnostics. If Proxima B has an atmosphere that can be measured, its detectability and composition will be strongly conditioned by stellar irradiation history, but that cannot be assumed from RV alone. It has to be tested with spectroscopy and careful retrieval. And this is where we need one clean sentence about the habitable zone that doesn't smuggle in hope as evidence. Proxima B's placement in the habitable zone is a geometric and energy statement, not a biological one. It tells us where temperatures might allow liquid water if an atmosphere exists and persists. It does not tell us that an atmosphere is there. It does not tell us anything about biosignature gases. It doesn't even tell us that the surface conditions are stable. In this system, the star's volatility is part of the habitability question, not an asterisk. So we narrow the bridge from planet detection to life search in a way that respects the micro-niche exoplanet data to inference to uncertainty to meaning. The meaning is not disappointment. The meaning is discipline. If we ever reach the point where we can take spectra of Proxima B's atmosphere, we will be looking for faint features, subtle absorption, slopes, hints. Those are precisely the kinds of signatures that stellar contamination can counterfeit. A spotty star can imprint wavelength-dependent patterns that resemble planetary signals. A flare can change a star spectrum during an observation and leave behind ghosts that look like chemistry. That's how a biosignature story becomes a false positive story if we rush. And that brings us to this section's required limitation, stated plainly: retrieval priors / model assumptions. Even when we eventually have atmospheric data, turning it into a claim requires a model, and models carry choices. Inference requires assumptions about geometry, temperature, structure, and how light interacts with matter. If those assumptions are too simple, if we treat a complex time variable star as uniform or a planet as a neat one-dimensional column of gas, our retrieval can return a confident answer that is confidently wrong. That's not cynicism. It's a known failure mode the model fits, but the world doesn't. So the cosmic checkpoint isn't the end of the story. It's the narrowing of the story into what can be responsibly said now. The title thread stays tight. The RV drift flipped across a decade of data, and the credibility framing is the entire point. The real reason is not a single culprit. It's a hierarchy of explanations that must be tested against confounders in the right order. Planet if it survives, star if it doesn't. Instrument if the star can't explain it. And always, always uncertainty carried forward, not hidden. Evidence moment the uncertainty bans. not as an apology, but as part of the picture. Proxima B shown not as a crisp globe of certainty, but as a world wrapped in shaded regions, what we infer, what we don't know, what could change, with better subtraction of the star. So we end this checkpoint with a conclusion that is both modest and consequential. Proxima B is a nearby target where the chain from detection to interpretation is unusually exposed. Every step is visible, and every weakness matters. That makes it one of the most important kinds of exoplanet, because it forces us to learn how to separate a planet from the star that hides it. And now we have to name what still stands between us and credible claims about atmosphere, and someday any serious discussion of biosignatures without self-deception. We turn to the measurable unknown we still can't subtract. The flare light is gone. The star settles back into its dim red steadiness as if nothing happened. But the record remembers. The decade-long radial velocity curve remembers. The uneasy moment where the drift seemed to flip remains on the screen like a question mark. You can't erase with confidence alone. In the end, that's what the system asks of us, not belief, but subtraction. Because the title isn't just a dramatic line. Flare over Proxima B, flip the RV drift. The real reason in decade data is a promise about credibility. It's a promise that we will not confuse a signal with a story, that we will follow the data into its discomfort and stop where the uncertainty begins. This last section is limitation heavy by design. Not because the science failed, because the science is doing what it's supposed to do, refusing to claim what it cannot yet measure cleanly. So we name the final question, in the simplest terms, that still respect the complexity what exactly is left in our measurement after we subtract the star. The word we keep returning to is contamination, not as an insult, as a description. The star's surface is not uniform. It has spots and bright regions, it flares, it changes with time. That stellar heterogeneity imprints itself onto starlight in wavelength-dependent ways that can masquerade as planetary motion in radial velocity and later masquerade as planetary chemistry in spectroscopy. This is the tension pair that holds the entire ending planet atmosphere versus star contamination. Detection versus interpretation, biosignature claim versus false positives. When we talk about signs of life on exoplanets, we're talking about faint differences, subtle signals, the quiet pull of a planet on its star, the slight dimming of starlight filtered through an atmosphere, a small absorption feature that could be a biosignature gas or could be something else. And Proxima Centauri is the kind of star that can make something else look convincing. So we keep the honesty tags close and we do not overreach. Stellar heterogeneity spots faculae flares can imprint chromatic signatures that contaminate both RV and any future atmospheric spectroscopy of an exoplanet. Without a quantified time-resolved activity model, attempts to infer subtle atmospheric gases risk false positives, because the star can write features into the data that look planetary. A credible path forward is not a single heroic observation, but a pattern of cross-checks, long-term monitoring, multi-wavelength diagnostics, and independent constraints that bound the contamination before we interpret chemistry as meaning. Evidence moment, the phrase, the outline, insists we see on the screen what we can't yet subtract. Not as a slogan, but as a measurement target. The measurable unknown isn't philosophical. It's a parameter, a bounded quantity. How large, how variable, how wavelength dependent is the star's contamination term across time? We name it exactly because this is the anchor that keeps the ending scientific time-resolved stellar heterogeneity contamination amplitude. That's the unknown that sits between us and everything people want to ask next. Between us and a confident statement about whether Proxima B has an atmosphere. Between us and any retrieval that doesn't quietly bake in the wrong assumptions. Between us and any future sentence that contains the words biosignature without immediately risking self-deception. And we don't soften it. We say the confounder aloud clearly as the outline requires. Stellar contamination spots and faculae heterogeneity, flares chromatic effects. This is the dominant uncertainty in the story. It is the reason a drift can appear to flip. It is the reason the nearest potentially habitable zone world can also be among the hardest to interpret. It is why proximity does not equal simplicity. 2 sentences of calibration, and then we return. On Earth, we can separate the planet from the sun with sensors placed in orbit with direct sampling with context we take for granted. For Proxima B, everything arrives as light, and light is vulnerable to mixing before it reaches us. So what does the ending mean? It means we have to treat the search for life on exoplanets as an inference problem first and a meaning problem second. It means habitable zone is not a conclusion, only a place to point our best skepticism. It means our most profound claims will be limited not by imagination, but by subtraction how well we can remove the star from the planet. The title's promise comes back one last time, not as a teaser, but as a frame across a decade of radial velocity data. The drift seemed to flip. The real reason is not magic. It is the uncomfortable overlap between a planet's subtle tug and a star's loud variability, plus the ways our models and calibrations try imperfectly to tell them apart. And if there is an atmosphere on Proxima B, if there are chemical hints that someday tempt us toward a biosignature interpretation, we will need that subtraction to be bounded, measured, repeated. Otherwise, the most exciting line in a spectrum becomes the easiest to fool. So we end where the science ends, with a named unknown that is measurable, and a quiet statement of what future data would resolve it. The measurable unknown is the star's changing face, quantified the amplitude and time dependence of stellar heterogeneity contamination across wavelengths. And the path forward is clear, even if the outcome is not long-term multi-wavelength monitoring, tied to RV and future spectroscopy, until the uncertainty on that contamination term stops being a shadow and becomes a number we can carry. The star dims again, the graph remains, and the final truth is both sobering and strangely beautiful. Before we can claim another world, we have to learn to subtract the light that hides it.